Hi everyone. I'm going to go through a quick solution of this problem I gave you and asked you to try last time. It's in an insulated container. 75 grams of ice at 0 degrees centigrade is placed in 825 grams of water at 25 degrees centigrade. What is the final temperature of the mixture? And notice it says an insulated container, so we can use the idea that the sum of heats is 0 because the system is isolated from the rest of the universe by the insulation. So we look at this and there are two possibilities. One is that the ice melts partially and in doing so brings the temperature of what started as liquid water down to 0 degrees centigrade, in which case you wind up with the final temperature being 0 degrees centigrade and an ice-water mixture. The other possibility is that the liquid water, what starts as liquid, melts all of the ice before it gets down to 0 degrees centigrade, in which case you wind up with all water at some temperature above 0 degrees centigrade. And so what we need to check first of all is whether the liquid water, what starts as liquid, um, can give up enough energy to melt all of the ice without reaching 0 degrees centigrade. And maybe it can because there's less ice than liquid water and there's a fair temperature difference, 25 degrees centigrade. But remember, the specific heat of water is much smaller than the heat of vaporization, latent heat of fusion of water. So we'll see. So in order to go to 0 degrees centigrade, the 825 grams of water can give up an amount of energy equal to, and this is Q total is not the heat that the water has, it's the heat that can leave it as it cools all the way down to 0 degrees. So that's equal to the mass times the specific heat times the change in temperature. The mass is 825 grams, so I'll put that in MKS units, 0.825 kilograms, times C, 4186 joules per kilogram Kelvin, or degree centigrade. I'll say, I guess I was saying degrees centigrade, so I'll say that. Times change in temperature, it's from 25 degrees to 0. I'll take the absolute value because I want to see what the magnitude of it is. So I'll say from 25 degrees to 0, the absolute value of that is 25 degrees centigrade. And put that in my calculator and come back in a second. So it's just under 86,340 joules. Now, if I figure out the amount of energy required to melt all of the ice, I will need the latent heat of fusion for water, which is 333,000 joules per kilogram. And so I figured that out. This is the heat to melt all the ice is equal to the mass of the ice times the latent heat of fusion of water, which is 75 grams, 0.075 kilograms, times the 333,000 joules per kilogram. And I'll put that into my calculator and come right back. So this is 24,975 joules to melt all of the ice. So the what started as liquid water has enough energy to melt all of the ice before getting to 0 degrees centigrade. So it's going to have an excess amount to warm the 75 grams of melted ice, of now liquid water, after the ice is all melted. So the sum of the heats is 0. And the heat, the energy added to the ice to melt it is the 24,975 joules. That's positive because it's added to the ice. Plus the heat that's added to the ice to warm it to warm the melted water now to whatever the final temperature is, which is going to be C of water, a mass of the melt water times T final minus T initial of the melt water, which is just 0, right? Because the melt water starts at 0 degrees centigrade. Plus C of water times mass of the what started as liquid, so mass of the initially liquid water, times T final minus T initial of the liquid water, which is the 25 degrees centigrade. And that whole thing is 0. And I want to solve this for T final, right? Because I'm trying to solve for the final temperature. And so I'm going to say, I'm going to get T final by itself on one side. So I'm going to say that we got T final times seawater mass of the melt water. So seawater mass of the melt water plus seawater mass of what started as liquid and I want to put everything else on the other side. So I subtract 24,975 from both sides, joules, and I add, see this has T final, that's 0, this has T final, so I add T initial liquid water times C water mass of the liquid water, or what started as liquid water, T initial liquid water, because that was minus, I added it to both sides, so I get a plus. And I want to solve for T final, so I'll divide on both sides by this whole thing. And I get, this is a little awkward. So I want to solve for T final. So I get that T final is equal to this stuff, minus 24,975 joules plus seawater is the, whoop, I'm off the screen, plus seawater is the 4186 joules per kilogram degrees centigrade times the mass of what started as liquid water was the 0.825 kilograms. So times 0.825 kilograms times the change in temperature, I'm sorry, times the initial temperature of the liquid water, which was 25 degrees centigrade. And I can use the 25 degrees centigrade as long as I'm solving for the final temperature in degrees centigrade, because notice I had all differences here. So with calorimetry problems, which is what these sum of the heats equal to 0 problems are called, I can use the Celsius temperature, because when I take differences in temperature, that offset that I talk about in the next lecture, due to the fact that the absolute 0 is not the 0 of the Celsius scale, that goes away. Anyway, just in case you saw the other lecture first and were wondering, so T initial of liquid water is 25 degrees centigrade. And you can see that from the units, the degrees centigrade cancel. Yeah, and you wind up with 1 over degrees centigrade in the denominator, which will give you final units of degrees centigrade. So this is divided by seawater, which is the 4186. joules per kilogram degrees centigrade times you've got mass of the melt water plus mass of what started as liquid water. I factored out the specific heat of water. So mass of the melt water is 0.075 kilograms plus mass of what started as liquid water 0.825 kilograms equals, and I plug that into my calculator. Be right back. And you wind up with 16.3 degrees centigrade, which would help if had a bit more light. So you can check that by going back over your calculation, plugging back into this equation. But assuming the algebra is correct, of course, that answer is going to be correct. Okay, well, thank you for your time, and I hope that was useful, and hope you have a good day until next time.